Today's lecture is on resonance. Resonance is going to be one of the most important topics in organic chemistry. Resonance is going to be probably 2 lectures long. We'll spend some time focusing on it. It's very important, and it will be with us for the rest of the semester. So what is resonance? So I have a little definition up here. When we consider resonance, we're usually considering resonance structures. Resonance structures are ways of representing molecules where electrons, typically in the p orbitals, are spread across multiple atoms. Okay, so we're going to see an example of this shortly. When we're talking about resonance, we need to be aware of delocalized electrons. Okay, resonance is possible because of delocalized electrons, which are electrons that are not confined to a single atom or bond. Okay, so we're going to be taking electrons and essentially moving them around a molecule in different spots. Okay, delocalized or electrons that are free to move around. So resonance is a net stabilizing phenomenon, and it's one of the 3 major considerations in organic chemistry. I would consider these 3 words the 3 major considerations in organic chemistry. We've already talked about induction with our polarity discussion. Electronegativity differences between atoms can create some induction or a dipole. Resonance is what we'll discuss today. Sterics we haven't really talked about yet, but sterics is essentially the size of molecules or the bulk associated with some molecule. Okay. Okay, so getting right into resonance, let's look at this simple example here to get an idea of what's going on. So we have this cation, this carbocation. We have a 3-carbon chain, 1, 2, 3, and we have this double bond here. Okay, so we have a double bond next to a carbocation. So what I'm going to do here is I'm going to draw a curved arrow, okay, a curved arrow. And I'm also going to write a little definition down here just so we're aware of what these curved arrows are. When I draw a curved arrow like this for resonance, and as we move into acid-base and reactions, we'll be seeing a lot of these curved arrows. So curved arrows like this show the movement of 2 electrons. Okay, so we're going to use this little curved arrow here to show the movement of 2 electrons. This is going to be maybe a pi bond or a lone pair. Okay, the movement of 2 electrons. In a future chapter, we will see the single-headed arrow like this, which is the movement of 1 electron. Okay, but we're not going to be using that one-headed arrow now. Just make sure your arrow does have 2 lines on it like this, and it's not a single-headed arrow, because that would be for the movement of just 1 single electron. Okay. So looking back here, I drew this arrow showing that this pi bond here, the 2 electrons in that pi bond are free to move to this position right here. And now if we did that, what would that look like? If we just moved those 2 electrons between these 2 carbons instead, well, that would give the double bond on the other side. Now this carbon over here has 2 hydrogens on it because it's a C double bond. So we have 2 hydrogens. So over here, there's still 2 hydrogens, right? We didn't touch anything with the CH bonds. But now this carbon only has 3 bonds, and it only has 2 hydrogens. Now this carbon is positive. Okay? So these 2 electrons in this pi bond, if we were to draw them over here on the right side of the molecule, we would essentially be flipping or switching the positions of both the pi electrons, the pi bond, as well as the carbocation. So this is what we would call resonance, okay? Resonance is when these delocalized electrons, typically in a p orbital, okay, so think pi bonds, are able to move next door to an adjacent atom or an adjacent bond. And by doing so, they create a net stabilization of the molecule. Okay, so this is the most simple example that we can draw, where these two electrons are simply hopping over and filling up this empty p orbital in this carbocation, thereby creating a carbocation on the carbon that's left behind. Okay? Now we could also flip it back. These two electrons could go back and give us the molecule above, right? So these two electrons are essentially hopping back and forth between either side of this 3-carbon chain, because these two electrons could be on either side. They could be filling up this p orbital over here, or they could be filling up this p orbital over here. Remember, looking at the right here, remember that a carbocation is flat trigonal planar geometry. It's a carbon with 3 things attached to it. So it's flat trigonal planar, and we have this orthogonal empty p orbital. Okay? And then remember those CC double bonds, they're also flat, and those pi electrons are in that p orbital, right? So those p orbital electrons in the double bond are jumping back and forth between either side of this 3-carbon chain. They can fill up this empty p orbital over here. By doing so, they create an empty p orbital where they left, and they can go back, right? So they can go back and forth. So this is what we would consider to be resonance structures. Sometimes you'll see them in brackets with arrows drawn between them like this, indicating that the structures are going back and forth. Okay. You may also see this notation where you see dots all the way around, and you could put a plus there, meaning that there's a positive charge and a double bond kind of going back and forth between these two CC bonds. Okay, so the double bond could be on the left, the double bond could be on the right, and vice versa for the positive charge. Okay, so you might see this notation down here. Okay, so we just need to be aware of the fact that when we have a double bond next to a positive charge, we'll see a couple other examples where we'll see resonance, but this is the most basic example. When we have a double bond next to a positive charge, those p electrons can move into that empty p orbital, and vice versa. They can go back and forth. So these two electrons in the pi bond are delocalized. Okay. Okay, now let's draw a couple rules here for resonance arrows. Rules for resonance arrows. Okay, let's start with 1. We want to avoid breaking sigma bonds. Okay, so when we're discussing resonance, when we're considering resonance, it's typically the movement of pi bonds or p electrons. Okay, so we're not touching the single bonds of the system. Okay. You also want to avoid exceeding an octet for the second row elements: nitrogen, oxygen, carbon, which is mostly what we'll be using, okay? So we never want to exceed an octet. So you never want a carbon with 5 bonds, You never want an oxygen with 10 electrons, carbon with 10 electrons. You could have a carbon with only 6 electrons, right? You could have a carbocation, but you never want to exceed the octet, okay? So let's draw an example here. Similar to the one we just have right there, I'm going to draw a different molecule. Let's put a double bond here. And we have a positive charge on this carbon. Now, remember, we don't touch the single bonds. We don't touch the single bonds. When we're talking about resonance, it's p electrons, pi bonds, and then either a carbocation or a carbanion, a positive or negative charge on carbon, okay? So this is very similar to the first example we saw here, right? It's a double bond next to a positive charge. So if we wanted to draw a resonance structure of this, we can take these p electrons and draw a double-headed arrow starting in the center of the bond, indicating that the bond could be moved next door between these two carbons. I'm going to highlight these carbons in red. We have these 3 carbons here. So these 3 carbons in red all have delocalized electrons around them, okay? This pi bond could be drawn between the first and second carbons here, or we could move it between the second and third carbons, which would give us a double bond in this position. If we pulled 2 electrons away from this first carbon, that means it is now positive because it is missing 2 electrons. Okay, it's missing its electrons now. So the carbocation essentially can shift over to this other carbon here. Okay, so these would be the 2 resonance structures for this molecule. Okay, we can draw the double bond as it is on the left, or we could draw it between the second and third carbon in this little chain here over here. Ultimately, there's not one set position for these 2 electrons. Those 2 electrons could be in this position, like on the left, or they could be over here on the right. That's why we consider the resonance structures, because those electrons are moving. Those electrons can be in multiple locations, okay? So we can only draw one structure at a time, but in actuality, these 2 electrons are shared between all 3 of these carbons, okay? Now, it's also important to consider which atoms have positive character. Which atoms have positive character? Well, any atom that we could draw a positive charge on has positive character. These 2 carbons in blue that I highlighted have more positive character than all the other carbons in the molecule, because we can draw resonance structures where we have a positive charge on these 2 blue carbons. Okay. Okay, so we saw, hopefully now it makes sense just working with a double bond next to a carbocation. Okay, this is probably the most basic type of resonance structure we can draw. Let's look at some other examples where maybe it's not a carbocation that we have, and discuss when we use resonance. Okay. So I'm going to draw a few arrows here. Let me do it in black. Let's consider this structure here. Oxygen. Okay. Very simple molecule, acetone. Okay, we just have a C double bond O with 2 carbons on the side, 2 methyl groups. So we could also draw a resonance arrow where we take this high bond here. Remember, we don't touch the single bonds. We don't touch any of the single bonds. We can take this pi bond here and put it right on oxygen as a lone pair. What would that look like? That would give us a single bond there, and then not 2 lone pairs, but 3 lone pairs on oxygen. Hopefully you remember from formal charge chapter, this would be negative up here, making this carbon down here positive. It's a good rule of thumb to make sure that your resonance structures all have the same overall charge. So if you start with something that's neutral, your resonance structures should be overall neutral. We have 1 positive, 1 negative, so overall neutral. Okay, so this is one type of resonance arrow we can draw. And this arrow is perfectly fine because we're not breaking any of our rules. We are not breaking a single bond, and we're not exceeding an octet for oxygen or carbon. Oxygen still has 8 electrons. It has 3 lone pairs and a bond. And this carbon down here has 6 electrons, which is okay. Carbon, you can have 6 electrons. It'll be a carbocation, and that's just fine. Okay. So these are 2 resonance structures of each other. So resonance helps explain some of the reactivity of molecules, because we can see from the resonance structure that this carbon highlighted in blue, this carbon has positive character to it, okay? Not only is there a dipole pulling electrons through induction towards oxygen, but there's also a resonance structure we can draw where these 2 p electrons are on oxygen as a lone pair, okay? Now, neither structure is fully correct, right? Neither one is fully correct. These p electrons, they could be here in a double bond. They could be up on oxygen. In actuality, they're shared between the 2, okay? That's why resonance structures are important. It shows us all the possible locations of delocalized electrons. What if we did this? What if we had the same structure, acetone, and I drew a curved arrow like this? I took these 2 electrons and I made them into a bond between carbon and oxygen. What would that look like? That would give us a triple bond here, oxygen with 1 lone pair. So oxygen has 3 bonds and 1 lone pair, so oxygen would be positive, and carbon with 5 bonds would be negative, but it's not possible as far as we're concerned in this class, okay? Carbon can't have 5 bonds. Carbon has 4 bonds, okay? So this is not good. This is incorrect down here, because we can't draw carbon with 5 bonds. We can't go triple bond with 2 single bonds, right? Carbon can't have 5 bonds because we break rule number 2. We can't exceed an octet, okay? So we can move electron lone pairs, we can move pi bonds, but just make sure whenever you do, you never exceed an octet, okay? That's really the most important thing to remember. Okay, let's look at a few other arrows. I'm going to draw a few more examples, and then we'll summarize sort of when we should be drawing arrows and some rules that we could follow. Okay, so we're going to see another one here, similar to the first one, but in this case, instead of a positive charge, it's a carbanion, it's a negative charge. So we have a negative charge next to a double bond. Okay. Okay, so one important term that we will use is the term allylic. And this means adjacent to a double bond. Okay, adjacent to a double bond, allylic. So this would be called an allylic carbanion. It's a carbanion, a negative carbon, adjacent to a double bond. Now this shouldn't be confused with the vinylic position, which is attached to a double bond. Okay. An example of a vinylic carbanion would be this. If we had a negative charge, I'll actually draw it on this carbon here. If we had a negative charge right on the double bond, that would be considered vinylic. If the negative charge is adjacent to it, it's on the next atom down, that would be allylic. Okay? Vinylic, allylic. Resonance, we are considering allylic carbocations and carbanions and lone pairs. Okay? Vinylic, we'll see in a different chapter. Okay, we'll talk about vinylic charges. But for this chapter, we don't have to be concerned with vinylic position, okay? Just make sure you don't confuse the two. So if we have an allylic carbanion, an allylic negative charge, how could we draw a resonance structure? Now, in the last case, what we did is we took this lone pair, took this pi bond, and we moved it to this position to fill that empty p orbital when we had a positive charge. That wouldn't work in this case because we have a negative charge with a lone pair here. That would give this carbon on the end 10 electrons. Okay, so we can't do that. So we have to draw a different set of arrows. What we're going to do, we're going to take this lone pair and turn it into a double bond. Okay, that would make this carbon up here have 10 electrons because it has a hydrogen here also. So if we did put a double bond here, this central carbon would have 10 electrons. So it says, hey, p orbital, p electrons, bump out of here, like get out of here. So these 2 electrons in this pi bond, they get bumped out. Where do they get bumped out to? That's what you have to consider. So I'm drawing the arrow. Now, this is the end. This is the terminal position. So we only have one option, which is to make them a lone pair on the final atom. We could also turn them into a bond if this chain extended, right? If this chain extended down this way, right? We could turn them into a bond potentially. But it's the very end of the chain. So the only option we have is to turn this pi bond into a lone pair. What would that look like? Let's draw what that structure would look like. It would have a double bond at that position, and then the negative charge at that position. So we essentially flipped the positions of the two, just like in the case of the carbocation. Okay. Again, you'll typically see them in brackets. I don't mind if you draw the brackets or not. But hopefully we can at least understand the arrows, right? And then going back, we can take that lone pair, turn it into a pi bond, and turn that pi bond into a lone pair. We're never exceeding an octet, and we're never breaking a single bond. all we're doing is showing the movement of pi bonds and lone pairs, okay? The delocalized electrons that are shared between multiple atoms. And again, you could see the less popular, but sometimes seen notation where you have a negative and then just a bunch of dots across those 3 carbons where that negative charge and double bond could be. Okay, but typically you'll see a structure on the right, and you just have to be aware of the fact that you have resonance. That negative charge could be on the left, that negative charge could be on the right. Same with the double bond. Okay. Okay, what about this structure here? What if we had double bond with oxygen, and then we had another double bond down here? Okay, what if we had that structure? I'll actually draw it a little bigger, make some space. Okay, so we have a carbon chain, double bond here, lone pairs. So we saw an example where we had a C double bond O. Okay, so the first resonance structure you can draw when you have a C double bond O is you can take the pi bond from the C double bond O and turn it into a lone pair on oxygen. Now you can't turn it into a lone pair on carbon. You don't want to do that because we don't want oxygen to have 6 electrons, right? Oxygen is more electronegative, but carbon is okay with 6 electrons, right? Carbon's just fine with 6. So we can take that P, those P electrons, that pi bond, put them up on oxygen as a lone pair, and that would be our first resonance structure. Now, this is the first example where we will see that we have multiple resonance structures that we can draw, okay? Okay, so what would that look like? That would be the single bonds are all the same, remember? You don't touch the single bonds, so you can always just start with that. Now we have 3 lone pairs on oxygen, and that gives us a negative oxygen and a positive carbon. Still have a double bond here. Now look what we have. We now have an allylic carbocation. We can take these p electrons and move them over to make a double bond at this position. That would give us another resonance structure where the double bond is now at this position, as indicated by our arrow, which makes the very end carbon positive. If we took electrons away from it, that's now positive. And we still have our negative oxygen up top here. If we wanted to draw arrows getting us all the way back to the first structure, we can take a lone pair on oxygen, come down here and make a double bond. That would give this carbon 10 electrons. So it bumps out these delocalized electrons, it bumps them out, says there's no more room here. Move on down. So those 2 electrons get bumped out and they make a double bond at this position, which brings us back to the first structure. So these are the 3 resonance structures we could draw for this molecule, okay? Again, just moving p orbital electrons, lone pairs, and pi bonds. It's all about lone pairs and pi bonds. Okay, so let's summarize all the different times when we should be looking at resonance. When is resonance possible? Okay. When do we consider resonance? Okay, first off is if you have a lone pair or a carbocation in the allylic position. Remember, adjacent to a double bond, right? So anytime we have a lone pair or a carbocation in the allylic position, okay? Secondly, anytime we have a lone pair adjacent to a carbocation, okay? We'll see an example of that. That one's pretty straightforward. Anytime we have a pi bond between polar atoms that are bonded together, like a C double bond O, okay? We saw examples of that. Pi bond between two atoms differing in polarity. Let's put it like that. Pi bond between two atoms differing in polarity, that would be like our C double bond O. And then finally, enclosed pi bonds in a ring system. This one's very straightforward. When I show you the example, you'll see how simple it is. But let's go through these and just put an example for each one. So anytime we have a lone pair or a carbocation in the allylic position, so that would be if we have positive charge next to a double bond, or if we have a negative charge next to a double bond, we have resonance, okay? So anytime you see this structure, negative or positive, next to a double bond, you should instantly think that a little clicker should go off in your head and you should think resonance, okay? Double bond next to a positive charge, double bond next to a negative charge. A lone pair adjacent to a carbocation, so something like this could be if we have just oxygen. Simple structure like this. If we had a positive charge adjacent to a lone pair, what would be a resonance structure we could draw? Well, we could simply take this lone pair and plop it down here as a double bond, right? We just drop that lone pair down. That gives us a double bond there. And it makes the oxygen positive instead of that carbon. And there's our resonance structure. If we want to draw arrows in the opposite direction, we could just show that pi bond becoming a lone pair. Okay? It's very important for your arrows to start the arrow in the center of the bond and then show precisely where those electrons are being dropped off. You will lose points on an exam if you're not precise with your arrows. Okay? You need to precisely show these two electrons right here are becoming a bond between these two atoms. If you drew the arrow like this, it would be considered wrong. These two electrons are not going to this carbon, they're going between these two atoms, okay? So make sure your arrows are precise. Number 3, a pi bond between atoms differing in polarity, right? We saw that with the C double bond O. Anytime you have something like this, you can draw a resonance structure where you take that pi bond and you just put it up top on the more electronegative atom, make it a lone pair, and that gives you that, right? Negative oxygen, positive carbon. And then drawing arrows to get back, you simply take that lone pair and turn it into a pi bond, okay? One thing you could do as you're learning, I've done this with students before, is you highlight the electrons that are delocalized. And we'll probably do this in the next lecture too, when we look at a couple more complicated examples. you can highlight the electrons that are delocalized, right? So you can say, oh, these electrons here, these are delocalized. These are the ones that can move around. So all these atoms, all these electrons that are highlighted in red, they're delocalized, meaning that they can move around, right? In the first case, we have these two electrons with a positive charge, so these two electrons can hop back and forth between these two carbons, delocalized. When we have a negative charge here, we have a lone pair that's delocalized, as well as a double bond that's delocalized. We have these two electrons that could be either a lone pair or a pi bond, and then the same thing down here, okay? Our fourth example is very simple and straightforward. We don't really need to discuss it at all, but I'll draw an example of it. This is a very common structure that we will get to know, benzene. We saw it last time. It's a 6-membered ring with 3 double bonds in it. Now, when we draw these 3 double bonds like this, they're alternating, right? Double bond, single bond, double bond, single bond. But in actuality, all 3 of these double bonds are in resonance like this, where we could also draw those double bonds in the other positions, and it's totally equal. It doesn't matter where we draw those double bonds when we have an enclosed ring system with double bonds in it like this, okay? Because those double bonds could be drawn in either spot. They could be drawn however you like, as long as they're alternating, because all of those double bonds are in resonance with each other, okay? That's not really something we'll need for this chapter so much, but it's just a good fact for once we get to study benzene rings. You should be aware of the fact that all 6 of those electrons are delocalized in that ring, okay? Okay, so if you're still not understanding resonance, that's okay. It is a strange topic. This is probably the first really strange and different topic in organic. So it's really just a matter of practice. So we're going to do some practice now. And then, of course, more review next time. We'll look at resonance in some more detail. And then we're going to do a whole workshop just on resonance. So 2 lectures and 1 workshop just on resonance, because it's very important to understand, okay? Let's consider this structure here. Let me actually put oxygen right up top. 6-membered ring with oxygen, and then a double bond next door. Oxygen has 2 lone pairs. So how would we draw a resonance structure for this molecule? Okay. So this would be number 1 on our list that we generated last time, which is a lone pair in the allylic position. We have a lone pair, right? Lone pair next to a double bond, okay? Again, don't touch the single bonds, just ignore them. Just focus in here on the double bond and the lone pair. They're adjacent to each other, so we have resonance. So how can we draw a resonance structure? Well, let's start with an incorrect example first. Maybe you started with double bond and you said, let's move this double bond. We have a lone pair up here. Let's push this double bond up this way. Now, if we put a double bond there, that gives oxygen 10 electrons, right? So we need to bump 2 electrons away from oxygen. Where do we put them? You would go like this, and you'd go, I can't really put them anywhere. I mean, we could put them here, but then this carbon down here has 10 electrons, so we're stuck. There's nowhere for those electrons to go. So we can't go that way. What if we took this lone pair and we dropped it down to make a pi bond here? That would give this carbon in red 10 electrons, right? So it has to bump some electrons down. So we take the pi bond and we bump it down. Okay, let's bump it down to make a C double bond C here. And then you should go, oh, well, that doesn't work because now this carbon on the very bottom has 10 electrons and we can't bump any away. So that arrow wouldn't work. So we have to turn this double bond into a lone pair on that carbon right there, on that carbon. What would that look like? Okay, we have our oxygen. Oxygen has one lone pair now and a double bond on that side, making it positive. We now have a lone pair and a negative charge on this carbon. Our charge is balanced. We have a 0 overall charge here, and then we have a plus and a minus for an overall 0. So our charges make sense. Nothing is exceeding an octet, and we didn't break any single bonds. Okay. Okay, so there's the resonance structure we could draw. Now we could draw even one more resonance structure, right? We could take this pi bond and we could just draw it back up here as a lone pair. What would that look like? That would give oxygen both its lone pairs back. It would give this carbon a positive charge. And it would give this carbon still a negative charge. We didn't touch that one. Okay. And then to get back to the very first structure, we're just going to turn this lone pair into that pi bond. And that gets us back to our very first structure. So all of these could be potential resonance structures of the molecule. Okay. None of these are fully correct. The true electronics of the system is an average of these three based on their overall impact. And that's something we'll discuss next class, is sort of the impact that each resonance structure has, talk about which ones are most important, which ones are less important, and sort of get an idea of the overall electronics of the system. But hopefully today, we can at least recognize these arrows as being good arrows to draw, good resonance arrows, because we're simply moving either a lone pair or a pi bond. We're not breaking any single bonds, and we're always making sure that we never exceed an octet. Okay, we never want something with 10 electrons. Okay, so what about this one? What if we had, let's see, we have an amide. That's a nitrogen next to a C double bond O. An amide or an amide. Okay, so we have some things going on here. We have a lone pair adjacent to a double bond, right? So that would be number 1 on our list that we made last time, right? We have a lone pair adjacent to a double bond. And we also have a double bond between two atoms of differing electronegativity, right? We have a polar double bond. So we have a couple different resonance structures we could draw here. Let's start with this polar double bond. We can draw a resonance structure where the pi bond could become a lone pair. Hopefully that you were able to see now after we've done a few examples. That gives oxygen 3 lone pairs, a negative charge, and it gives this carbon a positive charge. Now, if we want to go back to our first structure, we could draw this arrow, right? That would give us back to our first structure, turning the lone pair back into a pi bond. That's perfectly fine. But I'm going to draw this lone pair making a pi bond over here because that's going to give us a new structure. What would that give us? That would give us a double bond here. Nitrogen with 4 bonds is positive. Remember, formal charge. Oxygen is negative still. We didn't touch anything up here. Overall, our charge is still balanced, so that makes sense. Everything has an octet. Nothing has 10 electrons, so that looks like another good structure. Okay. Now, if we want to go back to our first structure, from this final structure we drew, we can draw some tandem or cascade arrows where a lone pair comes down to make a double bond. When that happens, this carbon has 10 electrons, so it bumps out these two right onto nitrogen as a lone pair. And that gets us back to our first structure here. So these 3 resonance structures are all good structures showing the electronics of this system. Okay. Again, next class we'll sort of rank these and talk about them individually. But for now, hopefully you can see those arrows, understand why they make sense, why they're good arrows to draw, and hopefully replicate it yourself. Okay, what if we had a long chain like this? We have a positive charge down here, double bond, double bond. So we have a positive charge in the allylic position. Hopefully we should be able to recognize this resonance structure where we take the double bond, move it over here to fill up that empty p orbital. That would give us this structure here. We have a double bond now on the end. This carbon is now positive, and we still have that double bond on the end that we didn't touch. Now we could go back like this, move that double bond back. That would give us back our first structure here. If we turn this double bond into a double bond on the adjacent position, but we're going to go the other way to get a new structure. Let's take these electrons in this pi bond and bump those down to fill up that empty p orbital. That would give us double bond here. We didn't touch that. Double bond here, and a positive charge on this end. If we want to go all the way back to our first structure, we can draw some cascading arrows where this double bond hops over, pushes this double bond over, and that gets us all the way back to our first structure here, where the positive charge is all the way on the left. So which carbons have positive character? Any carbon that has a positive charge on it in the resonance structure has some positive character. That's an important facet for future chapters. Resonance structures help show the electronics of the system. Resonance structures show which carbons could have a positive charge and which carbons have partial positive character, or in some cases, pretty much full positive character. Okay. So these 3 carbons in red have partial positive character. They're more likely to react with something that might be negatively charged. Okay, we'll get to that in a future chapter. One more example, and then we'll call it for today, and we will continue our discussion in the next lecture. Let's look at this one here. What if we have five-membered ring, double bond down here, double bond up here to oxygen, nitrogen here. What if we had this? What would be resonance structures we could draw with this molecule? Well, we have a double bond between two atoms with different electronegativity. We have a polar double bond, so we can manipulate those p electrons. What else do we have? Do we have a lone pair next to a double bond? No, we don't, right? So this might be a little deceptive. You think, oh, we have a lone pair next to a double bond, but they're not actually next to each other. There's this carbon in here. This carbon has a hydrogen, sp3 carbon. It's in between the two. So this lone pair is too far away. It has to be in the allylic position. This lone pair is not associating with this double bond over here through resonance. There's an sp3 hybridized carbon in between the two that are stopping those from interacting. If this double bond was over here in this position, they would be interacting, right? We have the allylic lone pair, but it's too far away. So don't let that trick you. Same with these two double bonds. These two double bonds, they can't interact. There's this sp3 hybridized carbon in between the two. Otherwise, we could draw resonance arrows, right? But you can't draw resonance arrows like this. You can't skip over that carbon, okay? You can't skip over those carbons. So ultimately, all we have is this one resonance arrow to draw. That gives us our five-membered ring. Let me try that again. Gives us our five-membered ring bonded to oxygen. Oxygen would have three lone pairs, be negative. The carbon would be positive, and the rest of the molecule is as it was. And that's all we could draw. We could draw the arrows to get us back to our first structure. That lone pair could come back down and make a pi bond. But these are the only resonance structures we have for that molecule. Okay. So again, just to summarize everything, when we talk about resonance, we're talking about the movement of delocalized electrons, typically in p orbitals. So we're thinking lone pairs, and we're thinking pi bonds, double bonds, okay? Whenever they're in the allylic position, adjacent to each other, we have resonance, right? If we have a lone pair or a positive charge adjacent to a double bond, for example, there's resonance. So we show that movement of electrons with a double-headed arrow. And when you draw those arrows, you have to make sure you don't interrupt the single bonds and you don't draw anything with 10 electrons. Okay. If you can do that, you're in good shape. If not, we'll continue working on it next lecture, lecture 7. We will continue resonance, and then we'll do a whole workshop just on resonance examples. Okay. Okay, I hope that was helpful, and I'll see you in the next lecture.